Okay, this is a problem involving the SL model. What we are given is that a pump is raising the pressure from the inlet, let's call it state 1 to state 2. The pressures are given, and also it's given that in an isentropic manner. So what we know is that S2 must be equals S1. We have to ask to find delta T and delta H, the change in specific enthalpy and temperature. Okay, so let's first list what we know about state 1 and state 2. State 1, pressure is given. And let's assume the elevation is 0. Then state 2, what we know is 5 MPa, which is 5000 kPa. And isentropic, that means S2 must be equals S1. That's the key to the problem. Okay. So when you use the SL model, let's recall the formulas for property changes in the SL model. So we know that the entropy change delta S is given by CV ln T2 over T1. And if entropy doesn't change, delta S equals 0. So immediately we know that T2 must be equals T1. So therefore, delta T equals 0, a very trivial solution. Now, how do we find delta H? We know that delta H equals delta U plus PV. That's the definition of H, if you recall, which is delta U plus delta PV. And delta U, again, using the formula is CV T2 minus T1. And delta PV is what? V doesn't change, so therefore V can be taken out of the delta. It'll be P2 minus P1. Once again, T2 minus T1 is 0 because we already proved that T2 and T1 are equal. So the enthalpy change reduces to this. So all we need to do is what is the specific volume. Of course, we know specific volume is inverse of density, and it remains constant in the SL model. We know density of water is 1000 kg per meter cube, but to verify, we can always go to the tables, and where the SL model, if you go to the tables, the SL models are in table A, common solids and liquids. If you click there, you go to find liquids on the right side, water. Notice water is given at several different temperatures, different values are given, but generally it's a standard to assume water density to be, density is in the second column, notice, rho is in the second column, about 1000 kg per meter cube. It's assumed constant in the SL model. But here, variation of water density with temperature is given, but whatever value you pick, your answer will not vary much. So taking 1000, what we get is the other pencil, 5000 minus 100 divided by 1000, which turns out to be about 4.9 kilojoule per kg. Well, now how do you verify this solution using test calc? For that, we launch the test calc, but what kind of test calc do you want to launch? System state or flow state? We obviously have a flow state involved with the inlet and exit, and then we choose SL model, and we go to the SL test calc tab and click run, and there we go. Select water, liquid water. Pressure at 1 is 100 kPa. Notice that the height is already initialized to 0. Without knowing the temperature, we cannot evaluate entropy. If you click calculate, you will notice entropy is not calculated. Therefore, you cannot use the fact that entropy remains constant. So take any temperature. For example, we say, okay, suppose the water is at 30 degrees Celsius. And you can show later that the answer is independent of the temperature. Then we go to state 2, and we know the pressure to be 5000 kPa or 5 MPa, and entropy remains constant, and height, the pump raises height, let me see how much, by 200 meters. So height changes a lot, but it has no consequence if you notice, because height doesn't enter in calculation of H or S. So therefore, oh sorry, S2, something went wrong. S2 equals S1. I wrote Z1. S2 equals S1. That's better. So that's why the temperatures are equal now. So what is delta T? We can quickly calculate delta T here. T2 minus T1. Of course, it will be 0. And what is change in enthalpy? H2 minus H1, specific enthalpy, which is 4.991, which is very close to our manual solution. So we verified our solution, but remember we assumed the temperature to be 30 degrees Celsius in state 1. Suppose you say, what about if the temperature was not 30 degrees? Suppose you say, okay, water temperature was 10 degrees Celsius. So to redo all the calculation, you change the value, and all you do is to click on this super calculate button. And just to show you where it is, this is the super calculate button. So just click there, and it will update all the results instantly. So if I click on super calculate, it is all done, and this time we can again calculate H2 minus H1, and you will see the result hasn't changed at all, exactly the same. So it's quite simple to solve a problem using SL model. The properties of SL model are in the table, as I shown. If you go to the test in the property tables, the first table is the common solids and liquids. SL table is right here, and then you can verify the solution using the SL test calc. So go ahead and solve a few problems, and you will find how easy it is to use the SL model.